Welcome to the video lesson for section 2.1. In this video lesson, we're going to be discussing quadratics. We're going to look at some properties and behaviors. Let's get started. For our function, we're going to let a, b, and c be real numbers. And if we do, then we have our general form of our quadratic, which is f of x equals ax squared plus bx. Again, a, b, and c are real numbers. This is our quadratic function. The graph of a quadratic function is always going to be yielding a parabola, and we can see what that looks like down here on our graph. We see it's got the traditional U shape. And then every parabola is symmetric to the line that is called the axis of symmetry. Usually it's referred to as the axis of symmetry, but it's also shorthand just called the axis. Then we have a point of intersection between the parabola and our axis, which is called the vertex. And we can see on this graph here, again, the vertex is where our axis of symmetry intersects our parabola, and it's going to either be the relative min or the relative max for our parabola. When looking at our quadratics, we have a couple behaviors we want to discuss. The first one is based off of our leading coefficient, which is going to be your a value. And your a value is always the value that is next to your x squared for our quadratic. If the leading coefficient is positive, what we're going to see then is that our graph is going to open upward. It also means that we have a relative minimum, or we have a valley. If instead our leading coefficient is negative, then we're going to be opening downward, and we're going to have a relative maximum. So based off our a value, we can already determine some of the behaviors or the features of our graph for our parabola. If we want to analyze a little bit more about what our a value does, we can look at a couple of examples here. So our simplest form is going to be just ax squared when a cannot be 0. And our parent function is going to be just y equals x squared. And as you can see, that is our red function in the very middle here. So this one is x squared. What we're going to do now is examine how a further affects our graph. For our first example, we can look at the 2x squared. And notice our a value is something greater than 1. When it is, we talked a little bit about this, we have a vertical stretch, or it's horizontally compressed a little bit. And we can see that our graph here, again, is a little bit more narrower, but it's also going to be a little bit taller as well. If we look at the other function that we have here, which is the 1/2 x squared, that's our blue function, we can see that we have something that's a little bit more vertically shrunk or a little wider. And we can see that the blue function is outside of our red function, showing again that's a little bit wider. So just to kind of summarize, if a is greater than 1, it's going to be narrower, or it's going to be vertically stretched. If a is something between -1 and 1, it's going to be a little bit wider or vertically shrunk. All right, for this example, we're going to be looking at our equation of x minus 3 squared plus 2, and we're going to try and figure out how we can take our parent function of y equals x squared and move it to end up representing this x minus 3 squared plus 2, and then take all of that and use it to help us identify the vertex and the axis of symmetry. All right, to begin with, we're going to look at this x minus 3 portion. So the difference with x minus 3 and just regular x squared is that it's exact same shape, but it's going to be shifted to the right 3 units. So we can see we have this dark blue shape here, which was our parent function of x squared. We're going to take that entire thing and shift it to the right to become our g of x function, which is now x minus 3 squared. So now the last thing we have to factor in is going to be this plus 2 on the outside. And then again, we'll use it to help us identify the vertex and the axis. All right, so we already know that the x minus 3 shifts it over to the right 3 units. And now the difference between our final function and g of x is the fact that that plus 2 is going to move the whole thing up 2 units. So we can see our greenish shape here, which is the f of x, our final function, which is x minus 3 plus 2. Now the thing we'd like to be able to connect is how do we look at the form of our quadratic and the vertex and the axis. And notice that we have the vertex, which is 3, 2. So what's the connection there? Well, some of you might have already seen this before, might be familiar, but this is called our vertex form. And for a vertex form, we always have h and k listed in our equation. And so in this case, let me write it over here, h and k, those values directly translate into our vertex. So the shifts, the horizontal and vertical shifts, are providing us with our new vertex. Because we are shifting to the right 3 units, and we're shifting up 2 units, that directly translate to a positive 3, 2 as our vertex. And then the x value of vertex is always going to be your axis. So then I know that the equation for my axis of symmetry is going to be x equals 3. Also, very important to remember that your axis of symmetry is always a vertical line, so we do need that x equals equation, not just the number 3. All right, here we can see your book calls it the standard form, but it's more commonly referred to as vertex form of a quadratic equation, is what we just mentioned. It is a times x minus h squared plus k. The convenient part here is we can pretty quickly pick out our vertex, which is the point hk. Again, that's your horizontal and your vertex, horizontal and vertical shifts. And then the axis is going to always be x equals whatever the h value is. Also, just to note, we are reviewing that if a is positive, it's going to open up, whereas if a is negative, it's going to open down. All right, the challenge here, though, is what happens when you have an equation that is not in that form? What do we do to get into that form? What we're going to end up doing now is we're going to review the process of completing the square to take our general form here and convert it into our vertex form to then help us identify the vertex and the axis. All right, let's go ahead and review our steps for completing the square. So the first step we need to do is we're going to group together our x values. So I can group together the x squared and the x. And then I need my coefficient for my x squared to be 1. So fortunately, these both have a common factor of 2, which means I can factor that out. And once I factor out the 2, I now have 2 times the quantity x squared plus 2x minus 1. All right, the next step now is to actually go ahead and try and complete our square. And in order to do that, we're going to take half of our middle term. And since our middle term here is 2, half of 2 is 1. And we square that, and we get a plus 1. Now we have to balance our equations. So I'm adding 1 on the inside, but what I'm really adding is this 2 times 1. So I'm adding a total value of 2. And since I'm making it 2 more on the inside of my parentheses, I'm going to be subtracting that same value on the outside so I have a balanced equation, because I can't just add something in without subtracting it. All right, now all we have to do is go ahead and factor our inside function. And conveniently, when we factor our inside function, the x squared plus 2x plus 1, we get x plus, again, half of a middle term, which in this case was 1. And if I simplify the outside, minus 1, and then subtract 2, I get negative 3. Okay, now that I have my vertex form, what I want to try and do is pick out my actual vertex. So if I look at this, this is going to be a shift to the left 1 and a shift down 3, which means that my vertex is going to actually be the point negative 1 and negative 3. My a value is positive 2, which means it's going to be opening up. So when I draw my parabola, I'm going to have a vertex at negative 1, negative 3, and I'm going to make sure that it's going up. And if you look at our final graph, you can see that we have exactly that. So again, you can see we have a vertex down here at negative 1, negative 3. Our axis is going through that vertex at x equals negative 1, and it's a positive parabola, so it's opening up. All right, here we have another example where we're going to try and find the vertex and the axis, but we don't have the right form yet, so we're going to work on completing the square. Our first step, just like it was last time, is to group together our x's. So I group together the x squared and the x. And I really need my value here to be a 1, but it's a 2. So I'm going to factor out a 2 from both terms. And now I have 2 times the quantity x squared plus 8x plus 31. All right, once I factor that 2 out and I have a value of 1 by my x squared, I'm going to go ahead and complete the square. In order to do that, we take half of your middle term and you square it. So half of 8 is 4, and if I square 4, I'm going to get 16. So I'm adding in a 16 on the inside of my parentheses. But remember, we have to balance things. So I'm really adding a 2 times 16, which is 32. And since I'm doing that on the inside, you can see on the outside, I've subtracted 32 to make sure that I have a balanced equation. All right, I can simplify the outside portion, and I can go ahead and factor this inside portion. So once I have factored that, you can see that we have x plus 4. And this value, again, is half of your middle term. Since my middle term was 8, half of 8 is 4. So I get that 4 there. And then 32 minus 31 is going to be negative 1. All right, when I want to use this to identify my vertex, I'm going to identify my shifts. So this positive 4 is going to tell me to go left 4. And this minus 1 will tell me to go down 1. So my vertex should be at negative 4, negative 1. Additionally, my a value is a positive 2, which means my parabola will be opening up again. So I'm going to have my vertex at negative 1, negative 4. Sorry, negative 4, negative 1. I'm going to make sure that my axis goes through x equals negative 4. And it's a positive parabola, so it's going to open up. And if you look at our graph, you can see all of those features there. All right, for our next example, we're going to try and graph this function. We're also going to find the vertex, and we're going to find the x-intercept this time. So when we want to find our vertex, again, we're going to go through the process of completing the square, which means we're going to have to try and factor to get our coefficient to be 1, right? We have a negative x squared. I really want a positive x squared, though. And I'm going to group my x's together first to kind of make that happen. So my first step then is going to be to take out a negative 1. And you can see that I've done that. So I took out that negative 1, which means I now have x squared minus 6x plus 7. And now I'm going to go ahead and complete the square. So I take half of negative 6, which was 3, or negative 3, and I square that to get a positive 9. But remember, this isn't really a positive 9. It's a 9 times a negative 1, so this is really a negative 9, which means to balance my equation out, I'm going to be adding 9 on the outside. When I go ahead and factor, again, when I factor, I get half of my middle term, so I have x minus 3. And when I combine my outside, I have 16. So the whole thing is negative x minus 3 squared plus 16. Looking at my shifts, I'm going to go to the right 3, and I'm going to go up 16, and I now have a negative parabola. So my vertex is going to be at 316, and it's going to be facing down. All right, for my x-intercepts, what I want to do is go back to the original form, and I want to try and factor this whole thing. Because when I factor it, I can find the zeros for my function, and those are going to help me identify my x-intercepts. So when I go ahead and I factor this, we end up getting negative x plus 7 and x plus 1 equals 0. And then to use those factors to help us find our zeros or your x-intercepts, I'm going to go ahead and set each factor equal to 0. And I get x equals 7 and x equals negative 1, which then translate into my two x-intercepts of 7, 0 and negative 1, 0. So having my vertex and having my two intercepts gives me a very, very clear picture of what my parabola is going to look like. And in addition, I know that it opens down, so I can have all that check out. And when I look at my final graph, we can see all of those features. So I have my vertex here at 316. I have my two x-intercepts. It's definitely opening down. And I now have a very accurate picture of my parabola. All right, for our next example, we're going to find the equation of a parabola with a vertex of negative 2, 1, and going through a point of 0, 1. If you look at the initial equation we have here, we have f of x equals a times x minus h squared plus k. We're going to try and identify as much information from this graph and plug it into that equation to help us solve for the remaining variables. The first thing we can do is looking at our vertex is always going to be identified as h and k. So I can go ahead and plug that directly into my equation for h and k. And when I do, I now have the equation f of x equals a times x minus 2 squared plus negative 1, or just minus 1. We have some additional information from our graph. We also have a point, 0, 1. We need to try and plug that in. Now, one of the nice parts about our equation is we have an x and a y, and don't forget, f of x is another expression for y. So I can plug my point in for x and for f of x. Let's go ahead and look at that. All right, so we now have f of 0 equals a times 0 minus 2 squared minus 1. This is my portion is going to just be 2 squared, which is my 4. And that's how I have 4a minus 1. And f of 0 is a fancy way of saying what's my y value when x is 0. Looking at my graph, my y value is 1. So we have 1 is equal to 4a minus 1. If I solve that equation by adding 1 and then dividing by 2, I get my a value to be 1/2. So now that I've identified my a value, the other things we want to make sure we include are your vertex. So I'm going to take my h and my k, and I'm going to take my a and plug them into the standard form to help get my final answer, which is going to be 1/2 x minus 2 squared minus 1. Now, if that's all we're asked to do, then that would be our final answer. If we need to go and turn it into our general form, we could go ahead and square out the x minus 2 squared, but generally this is going to be acceptable. Now, let's go ahead and try that again. We're going to try and find the equation for a new problem. This time our vertex is going to be at 3, 1, and we know that we have the point 0, 4. Just like with our last example, our first step is to take our vertex. We know that it is the variables h and k, and we'll plug that directly into our equation here. So what we now have is f of x is equal to a times x minus 3 squared plus 1, because we knew the vertex was the point 3, 1. I'm now going to use my point, and I'm going to plug in values from my point. If I do that, then we can see that we have f of 0 is equal to a times 0 minus 3 squared plus 1. So just to reiterate, my x value from the point was 0, so I plugged in a 0. And then this notation, f of 0, means what is the y value of that point. So if I plug in that y value, we can see from the graph it's a 4. So I'll plug that in for that f of 0, and I now have 4 is equal to, and if we do some simplifying, 0 minus 3, that's going to be a negative 3 squared. So that's how I get my 9a, and then I still have that plus 1. Looking at that equation, if I subtract 1 and divide by 3, I finally get my a value of 1/3, and that was that missing piece that we needed. So we can go ahead and we can take our a value, combine with our vertex, and plug them in to get our final equation. And remember, there are two forms of this. Initially, we get the more general form, which again, your book calls standard form, but I like to refer to as vertex form. If we needed to, we could go ahead and square out the x minus 3 and turn that into the general form, but I like the vertex form more. Based off of our a values, our parabolas are going to have a relative min or a relative max. In this situation, if we have an a value that is greater than 0, we're going to have a relative minimum because the parabola is going to be opening up. And that relative minimum is actually going to be our vertex as well. So to help find that coordinate, we have a formula of x equals negative b over 2a to find the x portion of your vertex. And we can then use that value with our equation to help us find the y portion. In this situation, if we have an a value that is in fact negative, so it's less than 0, then instead we're going to have a relative maximum. And that's going to happen because the graph is going to be opening down. So to find our vertex in the situation, because it is also a relative maximum, we use the same formula of x is going to equal negative b over 2a. And just like with our last formula, again, we have to have the form of ax squared plus bx plus c to be able to identify the a and b values to use this formula. Let's go ahead and use our equation. In this example, a basketball is thrown from the free throw line from a height of 6 feet. The question is, what's the maximum height of the ball if the path of the ball is modeled by the equation y equals negative 1/9 x squared plus 2x plus 6? All right, the path is a parabola. We can verify that it's opening downward because our a value is a negative. So that's verifying it's going to open down. Because it's opening down, we know we're going to have relative maximum. So far, everything checks out. The question is, what is that height? So to find that height, we're going to identify a and b and find our x value. And we'll interpret that and then use that to find our height. In this case, a is going to be our coefficient for your x squared, so it's going to be negative 1/9. And then we also know that b is going to be the coefficient of our x term, so b is going to be 2. Right, to find our x value, we know x is equal to negative b over 2a, so we have negative 2 over 2 times negative 1/9. This whole thing is going to simplify to be negative 2 over negative 2/9, which is going to be positive 9. Okay, so what that means is after 9 seconds, we're going to have our maximum height. But we still have to identify our maximum height. So what we're going to do now is take our time it takes to get to our maximum height, which is 9 seconds, and we're going to plug that into our equation. All right, so when we plug in our value, we have y equals negative 1 over 9 times 9 squared plus 2 times 9 plus 6, and that is going to equal 15. All right, we know that it is in terms of height, so we can interpret that as 15 feet, which means that after 9 seconds, we'll have a maximum height of 15 feet for our ball. All right, for this example, a fence is to be built to form a rectangular corral along the side of a barn that is 65 feet long. So let's highlight that real fast. We know that there's 120 feet of fencing that's available. The question is, what are the dimensions of the corral of maximum area? So that key term maximum area helps me identify that we might be using our equation we just discussed. We have an image here for our corral. So we know that one side is going to be x, the other side is going to be x because we have a rectangle, so those sides are equal. And then we also know we have 120 feet total. So if I take that 120 and subtract the two x's from my sides, then I get the width of my rectangle. To find the area, we know we're going to multiply length times width, so let's look at that equation. The area is going to be x times 120 minus 2x. If I simplify that, then I get my equation of y equals 120x minus 2x squared, which is a quadratic or a parabola. If I want to find the maximum area, I can apply my equation of x equals negative b over 2a. In this case, I want to identify both a and b. A is always going to be our term with our x squared, so a is going to be my negative 2, and b is going to be 120. So to help find my x coordinate of my maximum, we have x is going to equal negative b, which is going to be negative 120, over 2 times negative a, which is negative 2, and the whole thing is going to end up being 30. I actually already have an equation to help me solve for my other portion because I know what x is. I can plug it right in here to help me find the other portion of my dimension. I would do 120 minus 2 times 30, and I end up getting 60. Now, one thing I want to do as a quick check is make sure all of my values add up to be 120. So if both of my sides are 30, then I'm going to have 30 plus 60, and that is in fact 120. So when I go to answer my question of what's my maximum area going to be, I have a 30 by 60 feet pen.